Can you guys please confirm in the chat if you can hear me? All right, so Soumya, Narendra, can everyone please, if you can hear me, just type I can hear you in the chat. I just want to ensure that we are actually live. Sorry for the technical glitch, guys. Just if you can hear me, just type I can hear you in the chat.
Have you made it live?
Yes, Barney. Now they can. Now it's all live. So
but
I'm just gonna share this link in the groups.
But yeah, please.
Probably it may take 5 minutes for everyone to come in. So
Yeah, sure. So first of all, extremely sorry for that glitch. I had no clue because I usually, when I get into the training mode, I do not usually look at the messages because I get sidetracked. Our team looks into that. I'm sorry. It's one of those bad days for us. Okay. So in the interim, while everyone else joins, I can just tell you that there are a lot of learning resources coming your way. And do you know what? We have also launched the digital book. And this could be a one-stop solution for all of your students. Interview questions prepared by 138 data scientists who got placed through us. Digital book. It will be available from 24th August onwards. Mind map is available. Okay, case studies are already almost done. Virtual internship, priceless courses, and bunch of those. And well, this is one part. Let me go to mind map and let me also check. 73 people have joined. Yeah, sure, Dr. Srinivas. Today we will also post the link, and you all might want to join. Whoever wants to join can join, and we shall do that. And let us see how it goes.
So just a quick update, Barney. We have updated everyone in the WhatsApp group. So in maybe next 5 minutes, everyone should be back.
And a few of them are asking on can they join the WhatsApp group. So please, can you put that link, Enoch, so that people might, And now I think YouTube Live should be available. So
this was an error from the YouTube side, Barney. So I don't think YouTube Live would be there now. This was a bug from the YouTube side.
Oh, okay. All right. So we cannot do YouTube Live, is it?
Not today. Only for this day.
Okay. All right. So let's see. Yep. So you might want to ping. Yeah, we can, Sendil. We can put feedback. We don't take it on a daily basis, Sendil. On the last day we take it, but attendance we will post it. Yeah, certainly we'll post it. Okay, and then the WhatsApp link would be shared. And okay, let us get started. Let the people join in. AI and yeah.
Barney, just a quick update. Now the YouTube Live is also on. The glitch, I believe it's resolved.
Okay.
So you should be able to see it.
Sure. Let me check quickly. Oh, wonderful. Day 3 YouTube Live is there. Wonderful. Okay. So AI and deep learning. We started off with CRISP-DM. which stands for cross-industry standard process for data mining. And we started off by discussing about business problem. Recording the business objectives and business constraints is very important. Then data collection. We have data types, primary data sources, secondary data sources. We discussed about those. And then we also discussed about data cleansing. We discussed about all of these data cleansing techniques. And also we discussed about feature engineering on what do we mean by manual extraction and what do we mean by automatic extraction. And then we have data mining or machine learning. Okay, wherein we have supervised learning and unsupervised learning. And then before we get to supervised and unsupervised learning, for today, we are going to understand about model evaluation technique, which is machine learning primer. If you understand machine learning primer, I am certain that you will understand a lot of things. Simply, you will be able to understand how to handle any data mining project whatsoever. So let's get to machine learning part and we will understand more. Okay, let me also do one thing. I will have to expand this and then expand this so that I can collapse these and bring these to the bottom. Okay, so this is what I was discussing, and explaining, but then I I feel bad that I have to erase everything now and then redo it, but worth it. That's okay. Let me remove it. How did we get started? I was saying that even before you get started on any project whatsoever, you need to have historical data or the past data, which customer might have provided you, or you might have acquired the data from primary sources, or maybe you have purchased the data from syndicate sources. Say you have the data of a specific bank wherein you want to predict on whether a person will default on the loan or not. And you have age, gender, and income. And say you have data of 10,000 customers. And if you want to build your model, the first step is split the data into training data and test data. And when you split the data, while there are a lot of other techniques to split the data, most often than not, you do a random split. You randomly split the data into training and test. And when you randomly split, a few people split the data, or majority of them split the data in this proportion. 80% of the data would be in training, 20% of data would be in test. A few other people split it in this proportion wherein 70% of data is in training and another 30% of the data is in test. 60% training, 40% test, 50% training and 50% test, but not less than 50% in training. Why? Any competitive exam you speak about, any competitive exam for that case, you will prepare on a lot of questions and you test on only a fraction of questions. You usually train yourself for the competitive exam on thousands of questions. And when you actually go and appear for the exam, there might be 100 questions or 150 questions, etc. Right? So we will stick to 80% and 20%, though there is no hard and fast rule on how much you need to split, but the rule of thumb is you need to have more data in training than your test. Now, when you split the data into training and test, 80% and 20% or 90-10, however you want to split that, you will get the data here in training. You'll have output variable and you'll have input variables. So you have your output variable and you'll have your input variables. Since 80% of data would be in training, randomly, probably row number 2, row number 4, row number 5, row number 7, so on and so forth. So if you count these numbers, you'll have, say, 8,000 rows in training data, and remaining data would be part of your test. So you have your output variable and your input variables. Output and inputs. Whatever data is not part of your training will be part of your test. So you'll have row number 1, row number 3, row number 6, so on and so forth. When you count these, it'll be 1, 2, 3, 2000. Okay, randomly, whichever is not part of this would be part of this. So 80% of 10,000 is 8,000. So you have 8,000 observations in your training, and 20% of 10,000 is 2,000. So you have those 2,000 entries which are not part of training as your test data. Then you build your model using the training data. When I say build the model, all I mean is establish the patterns, learn the patterns among your y and x axis, or between y and x. If suppose this data is predicting on whether people are going to default on the loan or not, given the age, given the income, and given the gender, assume, right? So if the age is 32, income is 8,000 rupees, male, person will default. So your model has learned a pattern now that, okay, if I see this age, this income, and this gender, person will default. So it learns that pattern between y and x, or x's in this case. Multiple inputs are there. If the age is 42, income is 80,000, female will not default. So another pattern is what your model has learned. Building a model means learning the patterns. Patterns between y and x. These patterns are captured using your machine learning algorithm in the form of a mathematical equation. And any machine learning algorithm on the planet will do exactly this. It will just come up with a mathematical formula, mathematical equation to capture the patterns between y and x. That's it, simple. Okay, just give me a bit. I would take this down further. If I were to take, I think, yeah. All right. Now, when I say, okay, let me come up with an equation here. So after you build your model, what do? You test your model on the test data. And the equation would look like this. Y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. This says you think about this as logistic regression or some technique, and that some algorithm or technique, machine learning algorithm or machine learning technique, would capture the relationship between y and these inputs using this equation. Now let me take a toy example and help you all understand on how this happens. Say there is there is a data set which is provided to you, y and x. If y is 4, x is 2, say y is 10, x is 5, and then you have say 6 and 3, and say you have 8 and 1. Okay, and you're saying you're supplying this data set to your model and asking your model to learn the patterns, and your model started learning the patterns. And say your model has come up with an equation which is like this. This is the equation. I mean, you're having an equation here, right? This beta naught, beta 1, beta 2 are nothing but numbers like this is what you'll get. Now let me take the first row, substitute 2 in this. When I substitute 2 in this, you get a predicted value. It is always denoted with a hat on the top. And this predicted value would be, if you substitute this 2 in this, 2 into 2 is 4. You equate it to the actual value. Here you have actual y value. So when you try to compare these two, actual value is 4 here. So 4 is equal to 4. Wonderful. There is a match. Or if you say 4 minus 4, 0 is the error. Now let me take 5 and substitute 5 here, second row. When you substitute 5 here, 2 into 5 is 10. Predicted value is 10. When you try to compare it with the actual value, since the actual value here is 10, there is a match. Go to the third row, take this and substitute here. 2 into 3 is 6. And you try to compare it with this. Again, there is a match. Now go to the next row, substitute 1 in this equation, and you get 2 as a predicted value. When you try to compare it with the actual value, which is 8, there is a mismatch. What does this mean? This means that any mathematical equation that you get would capture all these patterns in a generic manner. Generic patterns are captured, not the specific patterns. Specifically, if you try to apply on each and every row, this equation may or may not hold true. But overall, when you look at the entire data set, it is going to work well. So this equation captured, or it has captured the generic patterns. In that way, any mathematical equation would capture the generic pattern. Would you ever get a 100% accurate model? I mean, can I ever get an equation which will work 100% correctly for each and every observation? No, we cannot. There is some underlying data issues. Yeah, your data is not that perfect. If it is that perfect, that means there is something wrong with your underlying data. There is something wrong with the quality of the data. You have to doubt the quality if your equation fits like a T to each and every row. Okay, so given this context, let's proceed further. Always remember, 100% accuracy is not right. You won't get 100% accurate models. If it is 100% accurate, that means something somewhere is going wrong with your data. All right. So what happens here is when you say building the model, it will learn all these patterns from your training data and it will come up with this equation. Now take this equation and test it on the test data. How do you test it? You take all of the inputs here and substitute these inputs in this equation. When you substitute this age, income, and gender details in this equation, you get predicted value, which is always represented with a hat on the top. And then try to compare it with the actual value. So take the first row, take all these inputs, substitute here. Say your model predicts that person will default. Then compare it with the actual value. Here, if the actual value says, yep, person defaults, then there is a match. Here person defaulted, predicted also says person will default, so there is a match between what your model predicted and the actual value, hence it's called as correct prediction. Then go to the next row. Take all of these inputs, substitute them in this equation, and then you get another predicted value. This time say the predicted value says person will not default. Then you try to compare it with the actual value, and if the actual value here says person will default, hey, there is a mismatch. Your model is saying that person will not default, but your actual value is saying that person has already defaulted. So there is a mismatch, incorrect prediction. In that way, try your model on all the 2000 rows and you will get 2000 instances wherein it will say whether the predicted value and actual value are same or not same. And how do you calculate the accuracy? Now you can calculate actually the test accuracy. Test accuracy on the testing data, the accuracy that you get is nothing but how many times did your model correctly predict out of overall predictions. Say your model predicted correctly 1400 times out of 2000 times. And if you multiply it with 100, you'll get it in percentage terms, and the percentage would be 70%. 70% is a test accuracy. Okay. Now the point is, are you happy with this accuracy or not? If you're unhappy with this accuracy, what you do is, with this information that you have, okay, you got some information, right? Take that information, and with this information in hand, go back and make changes to your model. When I say make changes to your model, all I'm saying is tweak your hyper parameters. So you'll have something called as hyper parameters. Every model, every machine learning model will have different set of hyper parameters. So take those hyper parameters and tweak those, make changes. Once you make changes, once again you build your model. Once again you'll get another equation. Come back and test on the test data. This time say your test accuracy has improved. Say it became 82%. Then can I say that test accuracy increased? Can I say that? Or can I not say? Yes, I can, but there is a caveat here. And the caveat is that, I'll tell you this. Say there are two students. One of the student got percentage of 98% in 10th standard. Say there is another student who got 92%. Student A and student B. When can you compare their results? You can compare their results if both of them are from the same secondary school of certificate, same board, or if both of them are from CBSE. You can compare the percentages, the accuracy percentages, right? Or if both of them are from ICSE, you can compare. Can you compare one student who is from ICSE got 92%, another student from SSC got 98%? Can we compare these two? Oh no, we cannot. Oranges and apples, how can you compare? On similar lines, when you're building your model, and when you're building your model twice, this is model 1 and model 2. You can compare these two models only when both these models are built on the same data. same training data. If there is different training data, you cannot, okay, you cannot compare these accuracies. To ensure that, ideally what happens is, you might, when you build your model, you will run all the lines of code at one go. Okay, say you have written 100 lines of code program in Python, 100 lines of Python program. Well, this hyperparameter tweaking will be somewhere in line number 20. You made the change and you run the entire thing. So that means randomly, once again, your data will get split into training and test. Once again, it will get split into training and test. To ensure that no matter how many times you randomly split the data, you have the same training data for model 1 and same training data for model 2. To ensure that we have the same data, we use set.seed. There is a concept called setting the seed. And within this bracket, you can give any number whatsoever. It doesn't matter. Say I give 10. When you give the set.seed and then when you split the data into training and test, whenever you run the entire code, it will look at this line that, okay, seed equal to 10. And this 10, do you know what happens? This 10 will hold all these numbers, that row number 2, 4, 5, 7, all these should be part of training data. Row number 1, 3, 6, so on and so forth should be part of the test data. Or if I give 19, for example, here, this 19 will hold all these numbers, that row number 4, 5, 7, 2, 4, 5, 7, etc. should be part of training data. 1, 3, 6, etc. should be part of test data. Instead of 19, if I give, say, 120, 120 will capture all these rows, 2, 4, 5, 7, all of these as part of your training. Row number 1, 3, 6, etc. as part of your test. Right? So that's how it works. That is the reason why people use set.seed, or setting the seed is what we call this concept as. Let me write down once again. You set the seed. Why do we set the seed? To ensure that how many ever times you split the data into training and test, you get the same data in training and same data in test. Only then can you compare the accuracies. Otherwise, you cannot. You should not, rather. You can, but you should not. Okay. So again, back to our discussion here. This time, say the accuracy increased to 82%. So what do? You again go back. Say you're not happy with this 82% accuracy. So again, you take this information and go back and change your hyperparameters and once again build your model and once again test your model. Building the model means the equation. Test it on the test data. And once again, you get accuracy. So this time, the test accuracy happens to be 91%. And say you're happy with this, you stop here. Say you stop here. But then a few people call this splitting the data into training and test and building the model on training and testing on test. And based on this information, if you keep tweaking the hyperparameter, they call this as information leak. They call this concept as information leak. That means information is getting leaked from the test data. It's something like this. There is a student. Okay, this student goes and appears for the test. And this student comes out and leaks the information that these are the test questions which have appeared. And if the same question paper is getting repeated in afternoon test, right? Morning test, afternoon test, assume, right? Morning test people leak the information, afternoon people take that leaked information, come back and again appear for the exam. If this process continues, then can you actually rely on these accuracies? Maybe someone got a good accuracy, 91%, because the person who has taken the exam in the morning has leaked the information to afternoon guy. Afternoon guy has leaked the information to the evening exam. Then if someone is getting 91%, how can you rely on that, right? With this analogy, what people thought is, no, this is an incorrect way of analyzing. And they thought test data or test paper or exam paper should not be leaked. You should not leak it. How would you leak it, right? Because you want to gauge the performance of students. So people thought, when we split the data into training and test, let us also have an intermediary split, which is going to be called as validation data. Okay, so you have training data, validation data, and test data. And here I would change this to 60%, 20% validation, and 20% test. Okay, now 60, 20, 20. Randomly you split again. Randomly 60% in training, 20 validation, 20 test. Now what you do is, here you'll have only 6,000 observations. Okay, and then let me choose a different color. Okay, randomly you split it 6,000, and here you'll have 2,000 observations, and here 20%, that's 2,000. After you build a model, you go and test your model on validation data. You'll not go to the training data. Okay, you'll test it on the validation data. And say validation accuracy was 70%. And say you're not happy. Then what do? You take this information, go back and tweak your hyperparameters, rebuild your model. Test your model on validation data. This time, say validation accuracy increased to 84%. Say you are not happy with this accuracy, then what do? With this information, go back, tweak your hyperparameters, retest your model. What are these hyperparameters? We will learn. Okay, we are too early to discuss those. We will discuss those later. And then you go here, rebuild your model, again test on the validation data. Say third time accuracy turned out to be 93%, and say you're happy now with the accuracy. Now what you do is, since you're happy with the accuracy, you take your model and test your model on the training data. Sorry, the test data. When you test your model on this test data, this time say you got a test accuracy of maybe 80% or 90%, whatever be it. That is going to be your final accuracy. This is as if you're testing it in real time. Why do we need to do all these things? Why is such a rigmarole needed? Because customer will ask you when you give this equation on, hey, did you test that? Are you sure it's going to work? How would you say, what would you tell to the customer, and how would you convince the customer that, yeah, customer, I tested it and it works, right? For that, first of all, you should be confident, and this is how you can be confident. And do you know what? Test data is like, for the very first time, you're exposing your model to the test data. It's as good as brand new data. We don't stop here. We don't stop here, friends. What we also do is we test our model on the training data also. You might say that, hey, I've built my model on the training data. Should it not give 100% accuracy? Same logic, remember, my dear friends. The equation that you're coming up with is a generic equation which captures the patterns of all these 6,000 observations. It's capturing the patterns of all the 6,000 observations basically. And you're testing it. When you test it, you get training accuracy. Now what you have to do is you need to compare both the training accuracy and test accuracy. Compare the training accuracy and test accuracy. We are not done yet. After this, we'll be done. If both these accuracy values are going to be high and close to each other, like this is 90%, this is 89%, or 95%, 93%, in that way, when both the accuracies are high and close to each other, you say that this is the gold standard, the right fit. This is the right fit. Scenario 1. Scenario 2. If the training accuracy is high and if the test accuracy is going to be low, then this scenario is called as overfitting. This scenario is called as overfitting. Overfitting is also called as variance. You fix these overfitting or variance issues through techniques called as regularization techniques. My dear friends, am I speaking about something which is specific to deep learning? Absolutely no. Are these going to apply to all the machine learning algorithms? Absolutely yes. What does the scenario mean? You have brought a lot of sample papers for the exam. It's a competitive exam. You brought a lot of previous competitive exam papers and you started preparing yourself. You are very good at memorizing, so you memorized the question and the options also. You by hearted to such an extent that if in the question I see that, okay, Ram and Sham have this much money, they have divided the money in this proportion, then at the end who got what profit. So if you have such questions, the moment you see Ram and Sham, you're like, you know that the option is B. Or the moment you look at certain numbers that Geeta had 5 chocolates and Sita had 6 chocolates. When you add these two, how many chocolates do you have? The moment you see 5 and 6, or the moment you see Geeta and Sita, you know that the option is C. If you by heart to such an extent, what would happen when you go to the main exam? If in the main exam, the questions are tweaked slightly, instead of Geeta and Sita, if someone says Nitin and Sharath, that's it. You'll be kind of confused. Oh my God, I never heard about these names in my exam paper. And you'll fumble big time. This is called as overfitting or variance. That means you are learning every row to the T. You're not coming up with a generic equation. You're particularly learning specifically for each and every row. That would be a disaster. Okay, you can, however, fix that. That's a big problem. Overfitting variance is a big problem in machine learning. And you can fix such issues using regularization techniques. The third thing is, if the training accuracy is low, then most often than not, your test accuracy also will be low. When will your training accuracy be low? You did not even prepare well for your competitive exam. You did not prepare well. So on the sample papers itself, you are getting less score. Then obviously in the main exam, you'll get less. Until unless some magic happens, right? Before exam, we go to, worship our deity that please help me pass this time. So until unless that kind of miracle happens, in test also you'll fumble. This scenario is called as underfitting. Or bias. This underfitting or bias problem is solved just by getting more data. For example, say you have 10,000 observations, maybe you need to have 20,000 observations so that more patterns are learned by a model. Maybe the number of sample examples are not sufficient to train your model. So you need more data. Or maybe you have taken only age, income, and gender, maybe educational qualification, number of, how much loan amount are you applying for? All those are also maybe important. So get that more data, more columns. Or remember feature engineering that we have discussed in the previous session? You need to apply that. So underfitting is not a big problem. You can easily solve it, right? So the fourth scenario doesn't exist, by the way. It should not exist. What is the fourth scenario? I did not prepare well for the exam, so my accuracy is low. That means my model didn't train well on the data. And however, when I started using that in the real world, it started working very well. Like I appear for the main exam and I get 90% marks. I mean, this scenario does not exist logically. If you rely on magic, I'm not sure, but logically it doesn't work. Okay. So this is the high level picture, my dear friends. If you understand this high level picture, wonderful. You'll surf easily. That means you understand everything about the high level picture. All right. Are we done? Not really, because accuracy, how do I calculate this accuracy? Are there any measures? Oh yes, certainly we'll discuss that. And one more thing I want to discuss here is accuracy percentage plus error percentage is equal to always 100%. Or accuracy plus error is always equal to 1. Right? Accuracy plus error equal to 1, or accuracy percentage plus error percentage equal to 100%. For example, if accuracy is 0.93, error will be 0.07. When you combine these two, you get 1. Or if the accuracy percentage is 93% and if error percentage is 7%, when you combine these two, you get 100%. Okay, now let me proceed further. And before that, why do you have this mind map? Can you not explain using this mind map? Oh yeah, sure I can. Let me. So machine learning primer. All I said is that you split your data into training, validation, and test. Use the training data to build your model. Use that model that you built on the validation data. Okay, test the model on the validation data. Why do you do that? Because you want to keep changing your hyperparameters and you want to figure out what will be the right setting which will give me the highest accuracy. And this hyperparameter tuning can be done manually or it can be done automatically. Automatically, if you want to do, there are techniques such as grid search, randomized search, optimized search, so on and so forth. Once you figure out the right set of hyperparameters which are giving you, well, which is giving you the highest accuracy, then you test it on the test data. When you test on the test data after getting the right set of hyperparameters, you get something called as test error. This test error is also called as generalization error. Okay, generalization error. Generalization error is written as bias error, that is underfitting error, overfitting error, and irreducible error. That's okay. Let's forget about that. Okay, so we built the model using the training. We tested on validation. We changed the hyperparameters to get the best setting, and then you tested on test data. Then what do? You compare the training error and test error, and if both of these errors are small and close to each other, it's a right fit. Do you know what? Previously, how did I explain? I explained in this way. Training accuracy and test accuracy, if both of these are high and close to each other, then I told this is a right fit. If accuracy is high, what will happen to the error? Obviously, your errors will be low. If the accuracy is high, then error should be low. If the accuracy is 90, error will be 100. If the accuracy is 95, error will be 5%. Simple, that's taken. And here you'll have test error. That means this is right fit. Then, if the training error is low and test error is high, and then how did I explain you previously? If the training accuracy is high and if test accuracy is low, then that means it is the model would underfit. Oh, sorry, my bad. Let me take this back. Okay, this is actually overfitting, right? This is called as overfit or variance. Training error is high, testing error is low. Oh, sorry, training accuracy is high, test accuracy is low. How do you put it when it comes to error? Training error is low and test error is high. This is called as overfit. So you know what? If your spouse calls you, if your wife calls you, these are the kind of mistakes you do. I mean, I was getting a call from my wife. Anyways, that's okay. So that's called as overfitting or variance. And you fix the overfitting issues using regularization techniques. All right. And the next scenario is this, wherein if both training error and testing error are high, what do I mean by that? In terms of accuracy, if your training accuracy is low and if your test accuracy is also low, both are low, that means it is underfitting. That means what? Error would be high. Training error is high and testing error is high. If both the errors are high, then it's underfitting or bias. How do you fix it? Transform the data, perform better feature engineering, increase the number of rows, observations, or increase the number of columns of features, and then you can fix this issue. Done. Oh, great thing. Yeah. Now, what are the different ways of measuring accuracies? That's another thing. And you know that error percentage with plus accuracy percentage is equal to 100%. Now here, to measure your accuracy, you have different ways. Okay, you have different ways of measuring the accuracy. If the output variable is continuous, you measure the accuracy or error in different manner. If the output variable is discrete in two categories or discrete in more than two categories, you measure in different manner. Let us look at how do you measure accuracy when your output variable is continuous. This is what we shall do. Okay, but even before we proceed further, of course, we lost some time. So we would not take 10 minutes break, but we would take quick 5 minutes break and we will get back. Just quick 5 minutes break. I also need some hot water. Yep. Let's take a break and come back, friends. All right. So, yep, there was a break for 5 minutes. So let's proceed further now and take this discussion forward. All right. Now, if your output variable is continuous, what do you mean by that? Say you want to predict on what will be the sales. Okay, assume that you want to predict on what will be the sales. And say you tried out two different techniques, two different machine learning techniques. You tried out something called as model 1 and you tried something called as model 2. And using these two models, you have done some prediction. And for this also, you have done a prediction. All right. And here you have done some prediction. For this model 2 also, there was some prediction. And you have actual values here. And say for the first month, I would say Jan 2020, you actually predicted that the sales will be 101, but actually sales was 100. And for the month of Feb, you predicted that sales will be 100, but actually sales was 101. Then for the month of March, you predicted that sales will be 99, but actually sales was 100. $100, 100 rupees, whatever be it. 100 crores, 100 lakhs, whatever you want to call it. And in the month of April, you predicted that it'll be 100, but actually it was 99 sales, $99 or whatever be it. Sales prediction. Here, what will be the error? So let me do one thing. It'll be easier if I remove this and put this somewhere here at the bottom. And here I would say error. Error is nothing but predicted value minus actual value. Predicted value minus actual value is 101 minus 100. You get 1. For the month of Feb, predicted value minus actual value, you'll get minus 1. 100 minus 101. Yeah. For the month of March, $99 minus $100, you get minus $1. Predicted minus actual. And for the fourth month, 100 minus 99 would give you 1. Put this aside. Now take the model 2, second model. And here also you have prediction which happened and predicted values are there, and you also have actual values. And then you have error. In that way. So you have model 2. You have the predicted value, actual value, and error. For the month of Jan, say the predicted value was 110 and actual value was 100. So the error will be 10. For the month of Feb, predicted was 100, actual sales was $110. So what is the error? Predicted value minus actual value, which is minus 10. And for the month of March, predicted value was say 90 and actually it was 100. So 90 minus 100 is minus 10. And for the month of April, predicted is 90, actual is, sorry, predicted is 100, actual is 90. So predicted minus actual will give you say 10. Now, If I calculate the average error, mean error, we'll give it a notation as ME. Okay. How would you calculate the average of these numbers? 1 minus 1 minus 1 plus 1 you add all the numbers and divide it by 4 divided by the total count. So you would actually get 0. 1 minus 1 is 0, minus 1 plus 1 is 0. So 0 by 4 is 0, right? You got 0. And mean error is 0. Here also, when you look at the mean error, you have 10 minus 10 minus 10 plus 10 divided by 4. When you do that, you get again 0. So mean error happens to be 0. For model 1 and model 2, mean error happens to be 0. If at all someone tells me that there are two models, forget that. I mean, assume that they're not showing you the underlying data and they're just saying that model 1 has mean error 0 and model 2 has mean error 0. If both of these models have mean error as 0, then which model is better? Obviously, both the models are better. Both model 1 and model 2 are better. Right? That's what you will feel. But then when you look at the underlying data, model 1 has less error and model 2 has more error. So which model is better? When you look at the underlying error values, model 1 is better because it has less error. But when you look at mean error, both seem to be the same. Why is this happening? Because of the positive and negative values getting cancelled out. How do I fix this problem? Okay, mean error is saying 0, but underlying data here error values are bigger. Here the error values are smaller. Then how do you fix this? You fix this using something called as MAD. MAD does not mean you all are going mad now. MAD means mean absolute deviation. Mean absolute deviation. Let's see. If I take all these deviations, errors are also called as deviations, and this is also called as, by the way, mean absolute error. You can call it as mean absolute error. Both mean the same. Mean absolute error, both mean the same. Now, if you take the absolute values here in this way, what would you get? Absolute value of 1 is 1, minus 1 absolute value is 1, minus 1 absolute value is 1, and absolute value of 1 is 1. Now when you take, you got now absolute error values or absolute deviation values. You got absolute deviation or absolute error values. Both mean the same. Now when you take a mean of these, what would you get? Mean would be 1 plus 1 plus 1 plus 1, all these divided by 4, and that will be 1, 4 by 4. So the mean absolute deviation or mean absolute error will be 1. Now let's see what happens when we take absolute value here. When I take absolute values of all of these, what would we get? Here you'll get 10, minus 10 modulus is 10, minus 10 modulus is 10, and here also 10. Then when you take an average of all these, that means 10 plus 10 plus 10 plus 10 divided by 4, then you get 40 by 4, which happens to be 10. So the mean absolute deviation or mean absolute error will be 10. Now when I want to compare model 1 and model 2, model 1 and model 2. Model 1 has a MAD or MAE. Model 1 has 1 and model 2 has 10. Given these, which model is better? That model which has the least error. Which model has the least error? Model 1. So which model is the best? Model 1. Less the error, better the model. But a few people thought, why do I use absolute value? Why can't I use square? We use square basically because we'll understand in mathematical foundations, because only when you have square, you can find the derivative. Okay. For those people who know math already, right? Modular derivative of a single number constant value is always 0. Okay. And if you have square, you can actually find the derivative easily. That's the reason why people prefer square. And also when you square it, say for example, error is 10. When I square it, what happens? It becomes 100. So you're in some sense, error is negative. Negative in the sense it's error is something that you don't want. You want high accuracy, you want low error. Error is something that you don't like. So penalty, from penalty terms, if you square it, it appears to be very big. Error 10 square, you're squaring it, it's appearing very big. So that's another reason why people do square. But of course, if that explanation is not clear and if it's not convincing, forget that. Okay, because there's a lot of math behind that. But this is fine. Now, a few people thought, why absolute value? Why can't I take a square? And they started taking square. That will also solve this problem of positive, negative values getting cancelled out. So let's look at this also, which is called as mean squared error. Mean squared error. So 100 minus $110, if this is $101 predicted value, actually it is $100, but your model predicted that it's $101. So when you subtract these two, predicted minus actual value, which will give you error, I'll write even that. Error is equal to predicted value minus actual value. Do you know what? Even if you write it as actual minus predicted, it doesn't matter. Why? Because at the end of the day, we don't go with the raw error values. We always square it or take an absolute. When you square or take an absolute, whether you write the error equation as actual minus predicted or predicted minus actual doesn't matter. Okay, that aside. So error here is $1. 100 minus 110, $100 minus $110 would be, let me put it in this way. This is $1. Here it will become minus $1. Then $99 minus $100 would be minus $1. $100 and $99. When you subtract these two, you get $1. When you square these, here you get $1 square. Units also get squared. Here you will get minus 1 square is 1. Dollar will become dollar square. Here also will become $1 square. Units also get squared, my dear friends. And then when you calculate mean of these squared errors, again $1 square plus $1 square plus $1 square plus $1 square divided by 4 would give you $1 square. And here it's $110 minus $100, so you get $10. Here you get minus $10. Here you get again minus $10. Here you get $10. And when you square all of these, when you square these, you get $100 square. $100 square. $100 square and $100 square. And then when you take the mean of these squared errors, you get $100 square. $1 square, $100 square. If I compare these two models, and if someone asks me, hey, is model 1 better or model 2? I would obviously say model 1 is better. Why? That has less error. But the units are getting squared. How do you fix that problem? Since units are getting squared, you fix that problem by taking a square root of these, and you call it as root mean squared error. Root mean squared error. When you take a square root of that, 1 square is 1, dollar square will become dollar. Here, 100 square root of that would become 10. Dollar square root will become dollar. Now, if you look at root mean squared error, root mean squared error, then which model is better? Model 1, because that has less error. Wonderful. Almost all the issues are solved using root mean squared error. That's it. Are you going to leave us for the day? No. Two more things. I can read your brains, okay? So two more things is that, see what happens is, I'll take this only as example. Why elaborate this or why exaggerate this explanation? Instead of dollars, if I represent this in rupees, what would this error be? Root mean squared error? 75 rupees, right? Instead of dollars, if I mention in rupees, it becomes 75 rupees. Now assume that there is a team which is sitting in US, and the chief data, not chief data, so say chief executive officer, CEO, asks the team in US, data science team in US, and hey, what is the error? They would say error is $1. They will say error is 1. And say there is a team in India. The CEO asks the team in India, hey, what is the error? They say 75. CEO would intuitively feel that team in US is doing a good job. Do you know what? They got an error 1. Team in India, bad job. They've got an error of 75. They would think in that way. There is scope for misinterpretation. There is scope for misinterpretation. To counter that, people came up with another measure, which is called as mean percentage error. Mean percentage error. See, percentage. Okay, let me ask this question. One is what percentage of 100? Yeah, can you all respond, please? One is what percentage of 100? Come on, I request everyone to respond. If you actually respect my training, I request you all to respond. Please, come on, everyone. One is what percentage of 100? Out of 100, if someone gets 1 mark, what will be that person's percentage? 1%, right? Obviously, it's 1%. In percentage terms, it's 1%. Okay, someone got 100 marks out of 100. What is the percentage here? Here it will be 1 divided by 100. And if you want in percentage terms, multiply it with 100, you get 1%. Here 10 is what percentage of 100? 10 is what percentage of 100? 10%. 10 by 100. And if you want this, you would get as what? 0.1, right? But then if you want it in percentage terms, it'll be 10% multiplied with 100. Simple. Guys, clear everyone? Okay, now this is how you calculate percentage. And that is exactly what is listed down here. If you want percentage error, you'll get $1 minus 1 minus 1 and 1, right? So if you want percentage error, then it is 1 is what percentage of 100? 1 by 100. Minus 1 is what percentage of 101? It's minus 1 by 101. Minus 1 is what percentage of 100? Minus 1 by 100. 1 is what percentage of 99? 1 by 99. And then simply, if it's mean percentage error, you take an average of these values. Same is the case with this model also. Right? Same is the case with the data which is here. You get the errors 10, minus 10, minus 10, and 10. And if you want percentage error, then it will be 10 by 10 is what percentage of 100? 10 by 100. Minus 10 is what percentage of 110? Minus 10 by 110. Minus 10 is what percentage of 100? Minus 10 by 100. And 10 is what percentage of 90? 10 by 90. That's it. You take an average of all these values. You take the percentage of all these values and it will be mean percentage error. Okay, it will be mean percentage error. All right, just a minute, friends. Sorry. And you know what? Sometimes what might happen is, say this is 100, just as an example. Okay. Suppose, just for our explanation purpose, say this is 101. If it is 101, if at all, and if I have 101, 1 by 101, what would happen here? 1 by 100 minus 1 by 100 will get cancelled out. Minus 1 by 101 and 1 by 101 gets cancelled out. So you'll get 0. To counter that, people came up with another measure called as mean absolute percentage error. Okay, it is mean absolute percentage error. So all you need to do is take an absolute of all these values. Then you get 1 by 100, 1 by 101, minus sign will go away, 1 by 100. And here you'll get 1 by 101. Then you take an average of all these. These are nothing but absolute percentage errors. And then you get mean absolute percentage error. Right? Here also you can calculate. There you go. So if your output variable is continuous, these are the various ways of calculating your error. Let me erase or let me remove, because here anyways we have those, right? So what did we discuss today quickly? We already understood about the business problem. We understood on how to collect the data. We understood about the data cleansing techniques and feature engineering. Then in order to get into machine learning, these techniques, neural network techniques, there are a lot of techniques, right? In order to get into these techniques and do practically using Python, we are ensuring that our foundation is so very strong that we understand those concepts very easily. So for that, we started off today with machine learning primer, and we split the data into training, validation, and test. We build the model using the training data, and we validated on the validation data, and we kept on changing the hyperparameters to ensure that we get the best model with the best settings. That model we tested on the test data, and we got testing error, which is also called as generalization error. Then we try to compare the training data and testing training error and testing error. If both the errors are small and close to each other, then it's a right fit. If training error is low, testing error is high, then it's called as overfitting or variance, and you fix that problem using regularization techniques. Then if both your training and testing error are high, it is called as underfitting or bias, and you fix that by getting more data or by performing better feature engineering. After this, we thought of evaluating the model performance. And if your output variable is continuous, you can either use mean error or mean absolute deviation or mean squared error, mean absolute error or mean squared error, or root mean squared error, or mean percentage error, or mean absolute percentage error. Okay, we will. I think we will not have time to discuss why discrete and the other stuff, but we will certainly discuss these things as part of tomorrow's session. And people who want to access this link, all you need to do is go to 360DigiTMG, go to mind map. The moment you click on mind map, there is a drop down here. Do a drop down and select AI and deep learning. When you click on this, you'll have this. Just click on that once, it would expand. Double click to collapse and double click to expand. Okay, and here is your mind map. You can zoom it, zoom out, zoom it, zoom out. Choice is yours. All right, then these videos are available on our YouTube channel. There are a lot of such videos coming your way. So please subscribe. And when you click on notify, the moment there is any such session which happens, you will receive a notification. And you need not even ask us on, hey, where do we get that? You just need to go to 360DigiTMG, scroll down completely, and you'll find, okay, scroll down completely and you'll find a YouTube channel button here. Click on that. And there you go. You'll arrive at this. There are a lot of playlists which are available. I recommend you watch that. And you also, I request you also do this. Go to our LinkedIn. Okay, and we will also post on the WhatsApp group if you may. You can ask your friends, colleagues, students to do that. And look at this. We have posted day 3 quiz already. These quiz questions, you have to respond in the comment window. Answer 1 is this. You need not worry on who is going to see, who is not going to see. Just respond. It's for your fun. And these questions can also be used for your own students when you train them in turn, right? And for people who don't have a LinkedIn profile, I recommend you to go to Facebook. And if you do not have LinkedIn, but LinkedIn is always good for professionals, right? For people like you and me. And on Facebook also, we would have posted. See, day 3 is already there. So you post it, you like it, you comment on it, go for it. It's yours. It's all yours. Okay. And follow without fail so that you receive all these kind of questions. Follow our LinkedIn page also to get all these kind of questions and free sessions, etc. And yep. So thank you all so much. And see you tomorrow. Until then, bye. Hope you have enjoyed the session. I'm sure you have. We have also given you the attendance link. Please give your attendance link because you'll be receiving certificate. Yeah. Yeah, LMS access will let you know. It would take probably next week for you guys to get LMS access. All these training slides would be there. Thank you, Satish. Thank you, everyone. I'm sure you enjoyed it. Thank you. Sure, Praveen. We shall do that. Thank you all.